Good morning. So, yeah, it's Thxgvg. It's what, Thursday, 6:30 p.m. You guys decided to come in and do some differential equations, which is commendable. So let's talk. So we have few concepts that we need to tie in together and understand. I just want to mention one more time the constant coefficients as the problem that it's easiest to work on and obtain a solution to differential equation. So say we have y double prime. Want to see something in my head. So
minus 2y prime.
Minus 2y prime. And then
minus 8y.
Minus 3.
How are you reading off homework? Which problem? Typical exam question says.
There we go.
Which homework problem?
Equal to 0.
3y.
If you can't see...
So it's minus 2y prime minus 3? 3y.
So 2y, yeah. 2y prime is good. You can see now. We can solve this problem by using characteristic equation. We know that from exam 1, chapter 2. And we achieve that by writing the r squared minus 2r minus 3. Oh, there's a y there. Oops. It's a 3y. So y double prime, y prime, and then y.
What would happen if the y wasn't there?
Hell on earth. You would actually move that 3. The question is what happens if that y wasn't there. You would have y double prime minus 2y equals to, and then you move 3 to the right, and then you solve this part using, right? So you still can be done, it's just, yeah. So this is what we have, and now we factor into r minus 3, r plus 1, and we have r is 3 and r is negative 1, which gives us the solution y of t, let's say, is c1 e to the 3t plus c2 e to the negative t. And this would be the standard way to solve the problem. But then you go, now what we, morning. Now let's say we had initial condition of y of 0 is equal to, let's say, 1 and y prime of 0 equals 0. Let's say we have these two initial conditions. Then we can push with our solution and find y prime of t as 3c1e to the 3t minus c2e to the negative t. Plug initial conditions in and figure out c1 and c2. So when I plug in the first initial condition, so y of 0 equals 1, it will give me 1 is equal to c1 plus c2. And when I use the second initial condition, y0 equals 0, I get 0 equals to 3c1 minus c2. So I plug in the first initial condition into the first equation, right? And then the second initial condition with a prime into the derivative equation. And I obtain the system. Now, the fastest way to solve this particular system is to add two equations. So we have 1 is equal to 4c1, and c2 is cancelled, from where c1 is equal to 1/4. And if c1 is equal to 1/4, then c2 better be 3/4, so they can add to 1. Now, this will give us the particular solution to differential equation. So we have the y of t, this would be the final answer. Y of t is equal to 1/4 e to the 3t plus 3/4 e to the negative t. Now, this is what we call particular solution. We calculated constants C1 and C2, and we're done. And you might say, well, yeah, this is what we did in chapter 2. This is too simple. And I would say, okay, now we're going to do the same problem using Laplace transforms. Because you have to be able to solve this particular problem using Laplace transforms, and you must obtain the same solution once you do the inverse Laplace. Otherwise, right? Good. So, in blue, we have same problem, which states y double prime minus 2y minus prime minus y double prime minus 2y prime minus 3y equal to 0. Y of 0 equals 1, y prime of 0 equals 0. Use Laplace.
Obviously, because there's initial conditions.
Conditions, yes. Morning, Kevin. So we have initial conditions and everything, so we can now use Laplace transforms to solve this problem. So what do I have? Laplace transform, you might not be able to see. You see there?
Yeah.
What's that? So Laplace would ask us to use the formula for the second derivative, and if you remember, that was the transform was s squared f of s minus s time the first derivative. In this case, the first derivative was 0, and then minus the function, which is just 1, the initial condition. And then we have minus 2 times s times f of s minus 1. And then we have minus 3 times f of s is equal to 0. So this is the transformation. We have y prime, the first 3 terms, and then 2 times the second 2 terms are all from the prime, and then the last term is transformation of, right? So now
S squared f of s minus s times y, not y prime.
no, it didn't go prime.
You see what I'm talking about, right? That s.
Yeah, you want to put 1 here and 0 there, which, oops, so function and then the derivative, right? What did I do? Yeah. Yes.
We only use the Laplace rather than use Laplace when it's like equal to cosine something. That's when looking at chart. S squared.
Yes.
Correct.
So if this was equal to anything on the other side, you
Other
would
than
transform
zero.
that in a...
But right now, we just, because then there's one constant that's going to we just add to the other side.
Yeah, so now we're going to solve for fs. So we have s squared f of s minus 2s f of s plus 2 minus 3 f of s equal to 0. So when we factor f of s, we get s squared minus 2s minus 3, which is a characteristic equation. Instead of, you've seen it in R, now it's in S. And then we are left with s plus s minus 2, which I shift to the other side as s minus 2. So s and plus 2 are the only ones that don't have f of s. S goes to the other side, becomes positive, and 2 goes to the other side, becomes negative. So f of s is equal to s minus 2 divided by s squared minus 2s minus 3. So that was our equation. And actually, this is the solution, except this solution is now given in a frequency domain. We want to transform this back into the time domain by using inverse Laplace transform. Now, we see that we can factor denominator into s minus 3s plus 1 and use partial fraction decomposition to break this apart. So we have a over s minus 3 plus b over s plus 1, which will give us as plus a plus bs minus 3b divided by s minus 3 s plus 1, and that needs to equal s minus 2 over s minus 3 s plus 1. So now we have equation that a plus b is equal to 1 and a minus 3b is equal to negative 2. If we subtract equations, a minus a is 0, b plus 3b is 4b is equal to 3, we find that b is equal to 3/4. And a better be 1/4 because they need to add to 1. So now my f of s is given as 1/4 times 1 over s minus 3 plus 3/4 1 over s plus 1. We hit both sides with inverse Laplace. So inverse Laplace of f of s is y of t. We copy 1/4, and then 1 over s minus 3 becomes e to the 3t plus 3/4, and then over here is e to the negative t.
Can you just scroll down 1 second before partial fraction decom? Oh yeah, right there. F of s minus 3, and you just copied that, and then all that equals s minus 2. I lost right where I was.
What I did is I picked all of the values that have all of the terms which contain f of s,
Oh,
factored f of s,
yeah.
and the leftover is s squared, right? S squared.
Yeah, minus 2s
2s,
minus
yeah.
3. I just didn't see where it equals s minus 2. Oh, so you had the positive 2 and that
Mm-hmm.
minus s right there.
Yep. So we started by first looking into, right, using good old method from chapter 2, where we did the characteristic equation and then used the initial condition to come up with a solution. And here it is 1/4 e to the 3t plus 3/4 e to the negative t. And then we did the same thing using Laplace, and we have the same solution. But why simple if we can complicate things? Solve the same problem using power series. So in red, same problem. We have the same problem. Y double prime minus 2y prime minus 3y equals 0, with y of 0 equals 1, y prime of 0 equals 0. Use power series. Yes.
I know in the notes we have to check to see if the equations analytical and if do you, I mean, if the coefficient of y double prime is 1, to bother with that, but if there's like an x in front of y double prime, you always check both sides.
Yep. We actually didn't get that far.
Oh, I just saw like a little.
Yeah. But the answer is yes. Use power series to solve the problem. The way we do it is we assume the solution y of t to be summation cn x to the n from 0 to infinity. And then we have y prime of t to be summation 1 to infinity of the derivative, which is n cn x to the n minus 1. And then y double prime of t to be summation 2 to infinity of n times n minus 1 times cn times x to the n minus 2. We replace all of these into the differential equation and make it nice and cozy, right? And then we see whether we need to shift the counter, or we need to use the peeling of terms and so on. So I have, instead of y double prime, I have the summation 2 to infinity of n minus 1 cn x to the n minus 2, and then I have minus 2 times summation 1 to infinity of n cn x to the n minus 1, and then I have minus 3 times summation 0 to infinity of cn x to the n equal to 0. So all I've done here is I replaced the three power series into differential equation where they belong. So at this point I see that all the exponents and the counters actually match, which is great, because this one is 2 and 2, and then 1 and 1, and then 0 and 0. So because they all match, shifting the counter would be enough. We don't have to do peeling terms, which is great. So I'm going to shift the counter we shift the counter, and we do that here and here. So when we shift the counter, you can go back and review the procedure if you don't know it. When we shift the counter, it will go back to 0, and since we are adding 2's on these ones, so it's going to be an n plus 2, n plus 1, cn plus 2, x to the n, minus 2 times, shifting the counter by 1 now, it's going to be n plus 1, cn plus 1, x to the n, and then the last one stays as is with a cn x to the n.
Because it's 0, right?
Yes. So now all of the all of the counters are 0, and all of the x are x to the n. So we can push all of this into a single sum, 0 to infinity. We are going to have n plus 2, n plus 1 times cn plus 2 minus 2, n plus 1, cn plus 1, and finally minus 3cn, all of that times x to the n equal to 0. We have the recursion equation here. When we take this thing, right, and set it equal to 0, because by the 0 product rule, we know that either this is 0 or that is 0. Now we don't want x to the n to be 0 because that is a trivial solution, so we want the coefficient to be 0, which gives us the recurrence relation. We have n plus 2, n plus 1, cn plus 2, minus 2, n plus 1, cn plus 1, minus 3, cn equal to 0. And at this point, we can start calculating stuff, right? We start with n equals 0. So the first one is n equals 0. When n is equal to 0, we have 2 times 1, C2, minus 2 times 1, C1, minus 3, C0, equals 0. So when n is equal to 0, we replace all n's with 0, and we have this first equation. And now we simplify this equation. So what I have here is 2C2 minus 2C1 minus 3C0 equals to 0. And we see that we have that 2 divide through by 2, we have that the C2 is equal to C1 plus 3/2 C0. Are you happy with this one? Just a little bit of algebra. When you plug in 0 for n, that's 2 times 1. 0 is for n, so we have C2 minus, again, 0, so 2c and c1, and then, yes?
Would you, because I know in the note and a couple of them, that they saw driven to the recurrence equations, like the one I did is c n plus 2. I got the same answer, but is there one that that's practical, or would you do that?
No,
And
whatever.
do that for all the n's, just do that line without like, the iron and if you do that only the 0,
Yeah, that's what we're going to do now. So the next one is n equals 1. We go, I don't know, let's go to n equals 17, see what the pattern is. I'm just kidding. So n equals 1. We have 3 times 2, c3, minus 2 times 2, c2, minus 3c1 equal to 0. So this is a 6c3 minus 4 times, and a c2 is c1 plus 3 halves c0 minus 3c1 equal to 0. And now simplify this. So we have 6c3 minus 4c1 and minus 3c1 minus 7c1. And then minus 6c0 equal to 0. When we divide by 6 everywhere, right, divide by 6. Over here we divided by 2. Divide by 6, we get that the c3 is equal to 7/6 c1 plus c0. So that's our c3. All right, so let's get n equals 2. So that's 4 times 3, c4, minus 2 times 3, c3, minus 3 c2s is equal to 0. So that's 12 c4 minus 6 times, and the c3 is 7/6 c1 plus c0, minus 3 times, and the c2 is c1 plus 3 half c0 equals 0. So I plug in everything, work it out, see what works. 12 c4 minus c1 minus 6 c0 minus 3 c1 minus 9 halves c0 equals 0. 12 c4 minus 4 c1, and then this is 12 minus 21/2 c0 equals 0. Divide everywhere by 12. c4 is equal to 1/3 c1 minus I have 21/2 and then 12/1. No, 1/12. So these guys cancel by 3. So that's 7/8 c0, and it's a plus. Over here?
Yeah.
Oh, I forgot the 7 somewhere? 7. So that's a 10. So 5/6. Yes, thank you. That definitely helps. So that's a C4. N equals 3. Maybe we can stop after that. I don't know. For n equals 3, we have 5 times 4, C5, minus 2 times 4, C4, minus 3 times C3 equals 0. So that's 20 C5 minus 8 times C4 is 5/6 C1 plus 7/8 C0 minus 3 times, and the C3 was 7/6 C1 plus C0 equals 0. 20 C5. Now when these starts canceling, this cancels by 2, so minus 20/6, no, minus 20/3. So yeah, 3 stays, okay. C1, 8 and 8 cancel completely, so minus 7 C0, I'll use it this time. This cancels by 3, so minus 7/2 C1 minus 3 C0 equals 0. Wonderful. This is amazing. No? I think it's amazing. But then you might beg to differ. And 20 C5 combine C1s. Oh great, we need a common denominator there. It's gonna be a 6, so that's a 40, and then 21. Is that negative 61 over 6? C1? Let's say it's good. Minus 10 C0. I'm going to divide by 20 to get C5 alone, and then really it's going to be this evil. So negative 60 also becomes 61 over 120 C1, and then plus 1/2 C0. Yeah, let's say it's good.
I think what at 4 in the top is what's it, minus 3 times 4. So I think it's 55.
No, this one?
Yeah, because it's n plus 2 minus that one. I'm just wondering.
Wait, plus 2? It's plus 1. It's plus 1. So that's definitely a 4 there. So that's an 8. Is everything good now? So let's say it's good. All right, so now what we do is we put all of this together into one long expression. So we start by, we have n equal to 0, and that's the coefficient for n equals to 0. And you also have x, this needs to be multiplied by x to the 0, which is 1, so we don't have to write it. So for n equals to 0, we just have this, c1 plus 3/2 c0. So as we start writing our solution now, well, this has to be y of x now because I used x up there. It's x to the n. I didn't use t to the n. So y of x is going to be, and we have our first term. So when we plug in for n equals to 0, right? So all I had was, what was it? C 3/2 c1 plus c0? Or c1 plus 3/2 c0?
C1 plus 3/2 c0.
Okay. And all of that needs to be multiplied by x to the 0, which is 1, so we don't have to worry about. So maybe I should label this, so this is the n equals 0 term.
And that needs to be multiplied by
X.
because you got the initial value?
No, we'll deal with that later. So now we have that's n equals to 0. Now the next term. The next term is when n is equal to 1. Actually, you know what? It's going to be easier for everyone if I just write out the power series first. So we assume the solution summation C0 of Cn x to the n, okay? And I'm going to write this out, and then we're just going to swap in all of the things that we need to swap in. So Cn x to the n is the power series that we assumed, and now I'm going to just expand this using just from calculus. So it's C0 x to the 0 plus C1 x plus C2 x to the x squared plus C3 x cubed plus that. Oh, I have C4 and C5, and so plus C4 x to the 4 plus C5 x to the 5 plus, and I'll put infinity there. So do we all see this? All right, now what I'm going to do is I'm going to plug everything in. So y of x is equal to, instead of, well, C0 is C0 plus C1x plus, and now C2, what do we have for C2? We have C1 plus 3/2 C0, and all of that is times x squared. Okay? Plus, instead of C3, what do we have for C3? 7 over 6 C1 plus C0 x cubed. Plus, what do we have for C4?
5 over 6 C1 plus 7 over 8 C0.
C0, and that's x to the 4th, plus, and now instead of C5, we have 61 over 120, C1 plus 1/2 C0 x to the 5 plus 3 dots. It goes forever. Now, pull all of the terms that have C0 together and pull all of the terms that have C1 together. That gives you two different power series. Bueno?
There's a question.
Yes.
If we know ahead of time that this is supposed to be e to the x, right, for both of them, why is first C0, there's nothing attached to that x to the first one? There's no C0, it's just a C1 picture. You see what I'm saying?
You're talking about this term?
Yeah, if it's e to the x, in the power series that e to the x goes up for every n, like there's an x attached to every n. Why is there no C0 there?
Well, what's the expansion for? So this is a side note now because there is a question. What is the expansion for e to the x? It is.
0 to infinity.
Yeah, but give me the string.
X to the n over. Oh.
Well, okay, fine. X to the n over n factorial, right?
Yeah.
So e to the x. So what do we have? We have 1 plus x plus x squared over 2 over 6, which is 3 factorial, right? Oh, we can use the factorials. Plus x to the 4 over 4 factorial plus dot dot dot.
And if there's a C0 attached to that, for both of them, if there's a C0 and a C1, why is there no C0 attached?
Well, what is the, now if we have e to the negative x? What do we have for it? Then you have, if you have negative x, then each of these x's becomes a negative x. So you have 1 minus x plus, this is still x squared over 2 factorial, but then minus x cubed over 3 factorial, then plus x to the 4 over 4 factorial.
Explain why there's no C0.
It's a combination of the two terms. So we'll have to figure out what we're going to do. So you can have, and then e to the 3x, which is the other one, is 1 plus 3x plus, and this is now 9x squared over 2 factorial minus 81, no, plus 81 x cubed over 3 factorial, right?
27.
The 20, oh yeah, 27, 81 is the last term. 27 plus 81 x to the 4th over 4 factorial plus going on forever. So in these combinations of these, they should emerge. Now this is a lot of labor to make it work, but that's what it is. So now I want to keep this, but I don't want it here. So how about we cut it and move it somewhere else. Let's leave it there for now, and then we'll figure out. So now what I'm doing is I'm going to split into 2. So all of the C0s together. I have a C0 and plus 3/2 C0x squared and plus C0x cubed and plus 7/8 C0x to the 4th and plus 1/2 C0x to the 5 plus going on forever. So those are all the C0 ones. And then all the C1, it's a C1x plus C1 x squared plus 7/6 C1 x cubed plus 5/6 C1 x to the 4th plus 61 over 120 C1 x to the 5. This is wonderful. And if there are no mistakes from before,
This is going to be the answer?
well, I'm trying to combine it into the answer so it looks the same as previous ones.
So you combine all the C0s and C1.
Yeah. Now I see the text missing.
Yeah, that's and the same with C1, there's no constant term.
1 plus 3/2 x squared plus x cubed plus 7/8 x to the 4th plus 1/2 to the 5.
I got it.
Yeah.
So we're missing an x and a constant. If we go to the original recursion relationship.
Did I miss something there?
No, but I'm saying, like, is it possible to set to ignore to ignore the c n plus 2 completely for now and just instead of the right two terms for c1? So like ignoring the n plus 2, n plus 1, c n plus 2, right? Ignoring that, solving for the c n plus 1, and then getting c1. Okay, so if you solve for c1, you're going to get negative 3 over 2 cn over n plus 1, right? And then you plug in 1, or sorry, 0, you're going to get c1 equals some combination of c0.
You got another hour left.
Well, in that case, you're
Then you're missing c1.
yeah. Then you'll not have you there.
Yeah.
So I plus 2 plus 2 plus 2 plus 2 plus 2 plus 1 plus 1. If I subtract, I will add everywhere. This is all. If all of these calculations worked out well, I hope they are. The only thing that I don't like is that I don't see the power series for E working on this one.
Maybe if you look this over, you get back to us on Tuesday.
Yeah, I can look over. I mean, we have to fix some of these coefficients. I have over 2. I have over 4.
Yeah, I think it was back in the previous in the fraction.
Yeah, I'll have to look into. I have to solve this one more time so we don't waste time here. But they have to. These things in parentheses here. They have to look like this. To be the form of that. Because those would be the power series that give you these two guys, which were the solutions.
But didn't we multiply you're talking about just the denominator, it's going to be multiplied then by 2 in the negative equation. In the original equation, they had y double prime minus 2y prime minus 2y.
Okay.
So it's like they're naturally going to be shifting the factors into.
Yeah, well, you have to have C0, and then you get the original problem, and then you work out the initial conditions when you get the solution.
So this whole problem took care of which sections, Professor?
Well, these so these three problems took care of everything. You had the Laplace transform, you had the power series, so chapter 3, chapter 4, and then from chapter 2, constant coefficients. The only thing we didn't talk about is variation of parameters and undetermined coefficients. Those are the only two things we didn't talk about.
AY double prime plus BY prime, CY.
So if you are inclined to try to solve a problem, you see what are all of the methods that you can use to solve that problem. And then making sure you're obtaining the same solution at the end, just like I did not. So, right, the first and second method matched 100%, and the third method in the power series is off. And there has to be some error somewhere that I compounded on top. Yes.
My question is, do you actually have the combination of
Yes. Yes.
So 4.1 is do the Laplace to find, using Laplace to find that thing you're not going to give us, the Laplace transform
Inside
Yeah.
the book.
Yes.
right, on the table.
So
And then the next
I will ask you to compute one of the Laplace transformation integrals. So what you have to know is you have to know that Laplace transform of a function f of t is given as the integral. Does anyone know it? E negative st times f of t dt, and the limits are 0 to infinity. Very good. So this is the formula that is not going to be given to you. You need to know this formula because this is the definition for Laplace transform. This is what you're learning in differential equation class. Now, the exam question will be use the formula to compute Laplace transform for, and now in class, I believe I did t, and I did maybe e and sine hyperbolic. So I did those three. What do you have? You have a t squared, you have sine and cosine, you have, so nothing that it's too crazy. It's just integration by parts or whatever else. Yes, use some.
So this one you're using Laplace to find the transformation.
No. You are using the integral to find the Laplace transformation of a function.
Okay.
So for, let's say, f of t is equal to, and let's say I say e to the 3t. So I want you to Laplace transform e to the 3t. Now, because you have tables, you would go into tables, you would use your eyes to look at the tables, and you would find that the Laplace transform for this is equal to f of s is 1 over s minus 3. So you would use your eyes and you would just write that and the problem is done. However, whatever I put over here would be scratched off on the table. So you would not be able to use the shortcut from the table. You are forced to use the integral to calculate that Laplace transform. Yeah. So that entry would be missing as a line. So imagine going to your chart and just white out any one of the lines, and you don't have it on the list. Now I will ask you to transform whatever I erase from the chart. I will ask you to compute that one on the exam. May it be t squared, sine, cosine, sine hyperbolic, cosine hyperbolic, e, right? It will be one of those basic ones. I will not definitely go with e3t cosine 5t, right? Because in that case, you would have to sit there and crank Calc 2 integral for 35 minutes. That's not the goal of differential equation class. So your job, right, as a student, is to learn Laplace transform definition formula, which is this one. Now, the table of Laplace transforms is given to you, which means that the problem, when I did it in blue, you didn't have to crank the formula for each one of these. You just used the table, and that was good. And also, when you got here, you didn't have to crank any integrals. You just use the table and you're done. But the question that is Laplace question, so obviously I have to make sure that you will have two Laplace questions, one to solve differential equation using Laplace, and then one to calculate Laplace transform. Maybe the third one to find just inverse Laplace of something, where you do the partial fraction for 15 minutes and, you know, done. It's very tricky to put this exam together because all of the problems are long. So I can't really, you know, place, just, you know, you have undetermined coefficients, variational parameters, procedure and the formula, and they take forever, both of them. And then you have Laplace transform and inverse Laplace transform and the solving differential equations by Laplace transform and the convolution, your favorite, right? And you have the power series. Each of these problems takes 20, 30 minutes, right? And we have hour and a half exam, which is why you see sometimes these tests with 4 questions on it, right? Because it's just so long. Unless I am asking very specific snippets, like for power series, give me just recursion equation. So whatever I did in red over here, just give me this thing here solved for Cn plus 2. So work out the algebra to make Cn plus 2 equals everything else, and then don't worry about these cases and putting the solution together at the end, because in the interest of time, right? I didn't say I will do that, but that could be one way to cut the work for power series in half. Solve the Laplace transform problem for something that it's quick to integrate. So if I'm drawing Laplace for this is the cheapest and the fastest problem you can get, because this one goes integral 0 to infinity e to the negative st e to the 3t dt. That's a basic U sub. You should be able to deal with this in less than 5 minutes. So limit b goes to infinity, integral 0 to b, and you have e to the 3 minus s times t dt. And now all you need to do is to integrate. It's a few steps only. So the integral is this itself divided by 3 minus s, computed from 0 to b. When you plug in b for t, you get the limit of, and I generally ask you to pull out the minus sign, so it's s plus, sorry, pull out the minus sign, so you get s minus 3, and then we are plugging in b divided by, what happened with my e? E to that divided by 3 minus s, and then b goes to infinity, and then when this is equal to 0, I just have minus 1 over 3 minus s. So now you have negative b on top. Negative b, you plug in infinity is negative infinity, e to negative infinity goes to 0, so the entire term dies, and you are left with negative 1 over 3 minus s. We switch this into negative 1 over negative s minus 3. Negatives cancel, and you got your s minus 3 for s larger than 0. You have to write that, because if your s is less than 0, then this s over here would be a negative, and then you would have a negative and a negative. The whole parenthesis would be negative, and this negative would make it a positive, and then this term would not go to 0. So this is actually part of solution. You have to be very careful. You have to write that, otherwise the points are gone. We'll talk about that again on Tuesday or whatever the review is, but you have to be careful that this over here is not there for decoration. It's a part of the solution, and it has to be there. And if you open your Laplace transform tables, you will find them, s larger than 0, s larger than 0, and so on. So the candidates for this kind of calculation, right, it's t squared, e to the at, sine, they call, is it kt or kt, cosine kt, and then sine hyperbolic kt, cosine hyperbolic kt. So these are the candidates, and one of these, I think that's, let me just take a look at the chart and see if I missed anything. Now the chart, yeah, good. Yeah, that's it. So one of these guys will be missing. One of these guys will be missing on your chart, and you will have to go and use the definition of Laplace to find it. Now, whatever is missing obviously will not be needed for whatever other Laplace stuff is around, because it's missing on the chart. You are supposed to use the chart for everything else on a test except for this particular problem, which is defining Laplace. Yes?
Are we
Da.
doing an electrical problem?
I know you love it, so why not? We can review that the next.
Just,
Yeah. So Kirchhoff laws, and then take two differential equations, unpack it into one constant coefficients, second order, and then hopefully you guys crank the undetermined coefficients or variational parameters rather than power series, let's say.
Can you just go over with the variables in the funnel? Because I know it's, so I think it's I just forget with the variables, like the coefficients of the I think you know what I'm saying. Like, you know how in oscillations, like and mass, for constant, no, it's mass, density.
Oh, what the letters mean?
Yeah, yes.
Yes, so capital I is the current, and that is going to be your differential equation. That's what you're looking for. You're looking for equation for the current. And in case of the alternating currents, you should have that answer to be some type of a wave. So the answer should be in terms of sines and cosines in that case. You have C, which is capacitance. You have L, which is inductance. And you have R, which is resistance. So we call these RLC circuits, resistance and inductance and capacitors. And we use Kirchhoff laws. So there's Kirchhoff law 1 and Kirchhoff law 2. First Kirchhoff law says that the sum of all currents entering and exiting the node equals 0. So that's technically the law of conservation. So all of the stuff in added equals all of the stuff out added. And then the second Kirchhoff law is regarding the voltage drop in any closed branch. And you follow through the loop, and the voltage drop on any of the components that are in line with the loop are negative. Any voltage drops that are against the line with the loop are positive. I mean, you can switch them, doesn't matter, because you can multiply the whole equation by -1. And that has to equal to the voltage provided by the source, which is also some type of a wave. So voltage might be 10 sine 3t or whatever. So once you push all of that together, you will get just a basic equation from... Now, I tend not to give the circuit problem where you have to set up two equations with the two loops, because there is the part where you are supposed to push two equations into one, which is chapter 5. So the next exam or the final will have that two-loop problem. Even though the two-loop problem was present in chapter 2, I tend to give that as a chapter 5 problem, because so you might be looking into just a very simple circuit rather than something that has to deal with stuff. Also, it's a circuits class where you actually see these things. Now the trick is that they actually allowed you to take circuits before you take differential equations. And then they say, well, the students didn't have the differential equations, so they might not be able to solve these things. Then they water it down in circuits. It's actually supposed to be, you must take DifEq before circuits, and then there should be just, blood and gore when you go to circuits. But it's not done that way. So over here, I would say, you guys will do that in circuits, and in circuits say, most of the students didn't take differential equations, so you end up not doing it anyway, and then it's a problem, right? Or doing it really, really poorly. So, I don't know. So that's why I moved the problem into chapter 5, where you actually, which is what we covered last time, you have two equations given to you that are, right, separated like this, right? You have two equations, so your Kirchhoff laws, this would be loop number 1, loop number 2, let's say, and then you push them together into one single equation of the double derivative, then you go and solve with whatever other method you can.
So just this again, understand the variables and hyperpolar problem and Kirchhoff's law.
Yes, so technically that's exactly what the spring mass thing was the last time. And then knowing that, right, just make sure that, if equation goes mass times x double prime plus, right, the mass doesn't have to be the first number given in the text. Because generally students will go, oh, yeah, so just, the numbers are 3, 7, and 5, and you put them 3, 7, and 5, where it's supposed to be 7, 5, 3, or something like that. So just be careful which variable goes where, and that is actually the part where you actually sit and look at the equation and you learn which variable has... I mean, in my case, the way I learn is I learn units more than anything else, because units, they never lie. If you know units, you know immediately. If they say, 15 microfarads, you know immediately it's a capacitance, because you know that the farad is a unit of capacitance, micro is 10 to the negative 6, great, 15 times 10 to the negative 6, F, and you have your C. It's that simple. Ohms for resistance, and henries for inductance. So you learn those, and again, it is application, but you have to understand that it's differential equations that give rise to all of our science and technology and everything else, because entire physics, all of the equations are derived through differential equations. So all of the formulas that you know and see, that's all DifEqs and work. So
you should teach the circuits class in the fall, or the spring. They'll give their teacher us all.
oh, really?
Probably for our class, the Wednesday night, long.
Wait, there's a Wednesday circle? I only saw
If they're going to move that to a Friday or Saturday, I can consider it, because I can't. I have calculus at that time. So.
There's a TBA.
Oh, no, well, it's a TBA for the Tuesday, Thursday as well.
Really?
Yeah, I heard they...
But you can just imagine this problem if I teach it. So maybe you don't want me.
Tuesday, Thursday.
Yeah, Tuesday, Thursday, it's a TBA staff, but I heard it's like the same professor every time, but it just never...
I heard that.
Okay, so we have variation of parameters, and we have undetermined coefficients that are left, and then also we have convolution, which is what you guys love. So we've seen the convolution example, one or two examples that are done. Again, depending on the functions that are getting convolved, you might use the U sub or integration by parts or anything. Can anyone off the top of your head tell me what is the formula for convolution in terms of the integral, as I have foreseen? Evan just left, so that's it, right? If Evan leaves, then the rest of the class just crumbles, right, and does not exist. So convolution formula is on your cover of the book, right, with all the other Laplace stuff. Convolution between two functions is denoted as the f star g, and it's the integral between these two functions. So integral of f of, and now we have this tau minus t, and then g of tau, and then d tau. Now, tau is just a variable that we use. You can, I mean, we could have used a different, like we could have used m, we could have used, you know, whatever other letter. It's just a Greek letter. It is actually Greek equivalent of our t, so it's just, you know, written this way. So it's like you're gonna write I, except you don't put the dot, you put the little squiggle on top. It's a tau. Happy? Yes.
Are you going to tell us which one is F and G, or do we have to...
Yeah, that is given to you, because you're supposed to compute convolution between two functions. Now, what I'm not telling you is the formula. You need to know to look it up on the Laplace table. Did you find the on a Laplace table formula for convolution?
Oh, yeah, it's right. But yes, it's right.
Where?
The tau right here.
Yeah, because you have to. Yeah, it has to be on a list.
It is. Yeah, it's F, S, G, S. It's wait,
That's the tau GT, I got the wrong one.
it's
Oh, right
F,
here.
T, G, T,
Yeah.
isn't it?
Okay. Yeah, whatever.
Yeah.
You can put on either one.
So that equation is going to be on the right, is that what you're saying?
Yeah.
Oh,
I'll put the same way as have it so.
That's not how to do it.
Yeah.
F of tau g t minus tau. This is the way your book has it. What were the? Okay, good. So now we pick convolution between two functions. So let's say f of t is equal to, I don't know, t, and g of t is equal to, I don't know, e to the t, whatever. And now you're going to plug into the integral and integrate. So the integral f of tau, so that's just going to be a tau, and then g is e to the t minus tau, and you have a d tau. Now if you know your algebra, right? You know that this is the same as tau times e to the t over e to the tau, d tau. And we see that this e to the t is in terms of variable t, and we can kick that in front of the integral because the integral is in terms of tau. So integral doesn't care about your e to the t at all. That's a constant. So we can kick e to the t outside, and you're left with tau e to the negative tau d tau as something that you have to compute. So now you will use by parts. So u equals tau dv equals e to the tau, e to the negative tau, d tau, du equals d tau, and v equals e to the negative tau over negative 1. So when you put the formula together, e to the t, what you're left with is negative tau e to the negative tau. Oh, the limit, 0 to infinity. We didn't put that. Gotta put that. What happened? 0 to t. You gotta use those. So 0 to t. And then minus and the minus gives you plus over here. And you have still integral e to the negative tau d tau, again 0 to t still on the integral. So now you have e to the t. When you plug in your t, you get negative t e to the negative t. Then you plug 0, the term dies. And then minus e to the negative tau from 0 to t. That's still left. So you integrate, right? You will get e to the negative tau over negative 1, but that's that negative there. So e to the negative tau, and you need to plug in this 0. So e to the t, negative t e to the negative t, and then this is minus e to the negative t, and now e to the 0 is 1, right? So it's a plus 1 over here. That's generally what goes wrong in these calculations. So now when I multiply through by e to the t, I get negative t e to the 0, which is 1, minus, again, 1, and then plus e to the t. So the convolution is e to the t minus 1.
What is that? So this is the thing that allows the cross function to be multiplied.
Okay? So in mathematics, you have mathematical forms that are mathematical form of a product. All right? So product of two functions. So you know that for the derivatives you have product rule. For integration you have integration by parts, because we just had an example, integral of t e to the t dt. You see that there is a product of two functions. So the product of Laplace transforms, right, is the convolution on the other end.
So that is this right there that relates to the maximum transform. It's the same thing as like UV minus the middle of UV, but
How did you say that for integration?
So first of all, multiplication. You have multiplication for numbers. 3 times 7 is 21. So that exists. Then you have multiplication with variables, which through exponentials. You have x squared times x cubed is x to the 5. Then we upgrade from, so we go numbers, then we go functions, then we go operators, right? The operators are limits. Limit times the limit is just, again, straight through multiplication. That's good, right? Just like numbers and functions and so on. But then we get into derivatives and integrals. For derivatives, you have the product, and that product is the product rule. For integrals, when you have a product, integral of a product, you solve that integral by using u sub. Or, not u sub, well, either u sub or by parts, but by parts is the actual one because that's the backwards product rule. And then you have the products with transformations, like Laplace transform. There are other transformations in mathematics as well. They have their own rules. So convolution is related to the product of Laplace transforms. So it's a mathematical form that we use to ease the calculations for or to make calculations possible in certain cases. So we know that the Laplace transform of convolution is equal to multiplication of two Laplace transforms. One more time, the Laplace transform of convolution is the multiplication of two Laplace transforms. The formula for that is Laplace transform of convolution of two functions is the product of Laplace transforms. I can't make it better.
No, I get that.
All right, good.
Also, a question. But about the project, again, assignment that we're going to. I'm going to put something, yeah, Tuesday, but it's going to be, I moved away from Laplace transform project into something else. It's,
You want hydrogen? I read it in hydrogen. So if you want the hydrogen, you want to just say the word. So you're ready to. I said or, right? The Laplace one is I think there's a landmine here that's not working. Definitely.
Good. So that was convolution. I think yes. And then we have partition process on the coefficients. It's like no one wants to go there. It's just endless calculations over and over and over again. Yeah, we did it in class yesterday, right? On Tuesday in class. Everyone was like, oh, really? We have it? Oh, no.
So we have the power series, we have, how about another power series since the previous one didn't go too hot? Or, I have another 15 minutes that I have to, I mean, that could leave like 3 or 4 minutes before.
I did have a question. The one example we did in the notes with undetermined coefficients, we can have like a repeated solution, so also this like just like a of x would be ax cubed plus bx squared plus cx. Why is that? Can you explain that to me?
Again, for differential equations, we are looking for independent solution. And anytime you have solutions that are dependent, we have to multiply them by whatever function works there and make them as independent solutions. So we know that we can check the Wronskian, right? And the Wronskian needs to be non-zero. If the Wronskian is non-zero, that means that the solutions are linearly independent. Linearly independent solutions mean that they are constant multiples of each other. Linearly dependent solutions are the solutions that are constant multiples of each other, which means it's the same solution. So if you run into a solution, so now we're moving to.
The solution is going to be ax plus b.
Let's go from scratch. So if you have y1 to be e to the 3t and y2 to be e to the negative t as we had earlier, these are linearly independent because they are not constant multiples of each other. If you have y1 equal cosine 3t and y2 equal sine 3t, also linearly independent. If you have y1 equal, let's say, x squared and y2 equal e to the x, also linearly independent. So all of these are linearly independent solutions, and you can always prove using Wronskian that they are linearly independent because the Wronskian will not be zero. But then you run into a situation where you have y1 equal e to the 3t and y2 to be 5e to the 3t. Now these are linearly dependent solutions because they are just the constant multiples of each other, right? You have that y2 is 5 times y1. And this is where multiplying by x comes in. So multiplying by x, over here, you will have to put this, when you put this, what we say superposition, which means you combine both equations into a single solution, y of t in this case. It will be e to the 3t plus 5t e to the 3t. And now these solutions are linearly independent. Now, if you check, right, you said, well, you know, you just added this t out of nowhere, right, just to make it fit the theory, right? Well, if you actually check the solution back in the original differential equation, you see that the solution will work. So I can give you immediately example of this. So say you have y double prime plus 2y prime plus y equal to 0. Now, characteristic equation over here is r squared plus 2r plus 1 equal to 0. This compresses into r plus 1 equal to 0, which is just r equals 1 with multiplicity 2. So your y1 is e to the t I guess, or x, whatever, and y2 is also e to the t. So, negative t, I meant, because this is negative 1 over here, if you pay attention at all. I understand it's early, it's okay, fine. 6 p.m., right? On Thursday, yes.
It's a multiplicity when back to the t over negative t?
Yeah. So now when I plug in into the solution, I will have C1 e to the negative t plus C2t e to the negative t. So that was a repeated solution. Now, well, give a sec. So now I'm getting there. So now if you are to plug this back in, you'll say, well, yeah, you got that, but see, you put this out there out of nowhere, so how do we know that that actually works? Well, there is a y prime and y double prime and some time that you're going to invest in your life to plug everything in and to see that it works. Then, from these solutions of e to the t and so on, we jump into the new realm where your y could be, let's say, t squared, and then, so y1, and the y2 is maybe 3t squared. Well, when you have polynomial solutions, you are multiplying by ln t. So y of t would be t squared plus 3 ln t times t squared. So you have to learn the forms of which particular function is the one that, in quotes, fixes the problem of linearly dependent solutions and makes it linearly independent solutions. So for exponential function, you are multiplying by t squared, t cubed, as how high you have to go. And for polynomial solutions, you are multiplying by ln, and so on. So there are charts and things. Generally, we just need these two because they are in our, dare I say, mundane problems, are the only ones that come about. But then there is a table out there where you find all of these guys that work. So anytime you have a repeated solution, you have to follow it with, yes, with this fix that will make the solutions linearly independent. Fair? Good. So power series tend to be, right, the heavy hitters for this particular exam. Also, integration by parts from calculus 2 and partial fraction, decomposition from calculus 2. You don't need, the trig sub and that kind of stuff. But then you need u sub, you need by parts, and you need partial fractions. You need power series, right? So you see that this is really Calc 2 heavy, especially this exam. You need knowledge of algebra to shovel those FS terms, right? And then hopefully unleash partial fraction decomposition, and in 2 minutes get the solution for from the inverse Laplace. The last formulas we covered in Laplace transform, the Laplace of the derivative and the integral, right? Those formulas are also on your list of Laplace transforms, like the integral of f of t divided by t and the derivative, the t times f of t. Those are convenience formulas. You can go through the horror of computing Laplace transform for it, or you can use the formula to plug things in. It's just knowing how to peel off a term, whether it's integration for over t or differentiation with times t. Yes?
So you can, you don't have to be able to calculate t is 4 times e to the 18. Or like, you know what I'm saying? Like,
Yeah.
since I'm reading the chart, it's following.
You follow the chart, yeah. But there is that matter of Laplace transform, right? Laplace transform of t e to the 4t cosine to the 7t, right? So, yeah, good luck finding this in your chart because it's not there, right?
So how would you attack? You'd have to break that down.
Well, isn't t equal to in the chart and then a times 17 in the chart for the decomposition or
The convolution would have to be here, and then multiplication of Laplace is on this side. So it's not. You have it 100% backwards. so what you do here is you realize that you have t times something that is in a chart. And you are using the formula for the Laplace transform. Now this formula is given in the chart. Which color should I use to write the formula? Green. Laplace transform of t, f of t is equal to fs prime. Right? Is that somewhere on the chart?
That's prime, right?
Yeah, right there.
T f of t minus f prime of s.
Yeah. Oh, I forgot the minus. Oops. Right? So now, you know, by looking at, right, this t matches t.
Right.
So now you can look in your chart and find that in the chart, the e to the at cosine kt, what is equal
S
to?
minus a over s minus a squared plus b squared.
Right? You see, so the chart gives you that, and you can, you know at that point that negative f prime of s is equal to s minus a, so that's s minus 4 divided by s minus 4 squared plus 49. See that?
Yeah.
Oh, yeah. Oops. So f of s is this, and then you take derivative of this, and you make it negative, and then you have what the
Take
Laplace
derivative of the s minus
of
the
yes
thing.
of the whole thing. So now the f prime of s is equal to, you have the whole denominator, right, which is s minus 4 squared plus 49, everything squared, and then on top you have s minus 4 squared plus 49 times the derivative of the top, which is 1, minus s minus 4 times the derivative of this, which is 2s minus 4. Is that good? Yeah, let's say it's good. So f prime of s is equal to, we have s minus 4 squared plus 49 minus 2 s minus 4 squared, and then s minus 4 squared plus 49, everything squared. And now you see that this and this combine because they are like terms. and you get that f prime of s is equal to 49 minus s minus 4 squared over s minus 4 squared plus 49, everything squared. And now you need to put the minus in. So now minus f prime of s is, and that will swap the sides here, s minus 4 squared plus 49 squared. So what is the Laplace transform of t e to the 4t cosine 7t? It's equal to s minus 4 squared minus 49 divided by s minus 4 squared plus 49, everything squared. Or you can go and do the integral. All right, I have to fly to the next one. I will see you all Tuesday. Keep practicing. Enjoy the rest